Hello, everyone. Welcome to Chapter 11 of our chemistry lecture series. Today's topic is gases. I'm Dr. Luning He. In this chapter, we'll explore the physical properties of gases, how they behave, and how we can apply this knowledge in healthcare and everyday life. Let's start with a fun but practical question. How long can a straw really be? When we drink from a straw, we're not actually pulling the liquid up. What happens is that we reduce the pressure inside the straw, and atmospheric pressure pushes the liquid up. This simple concept is deeply rooted in gas behavior and pressure. Now suppose we had the perfect straw, rigid walls, perfect seals, and even a perfect vacuum. You might think we could make it infinitely long. But in reality, even with all those perfect conditions, a straw longer than 10.3 meters or about 34 feet won't work. Why? Because the atmosphere can only exert so much pressure to push the liquid up. So what is pressure? Pressure is the force that gas molecules exert when they collide with surfaces. On Earth at sea level, atmospheric gas molecules exert a pressure of about 101,325 newtons per square meter or 14.7 pounds per square inch. This pressure is what pushes the liquid up the straw when we lower the pressure inside it. When you place a straw in soda and do nothing, the pressure inside and outside the straw is the same, so the liquid levels match. But when you suck on the straw, you lower the pressure inside. That imbalance causes the greater outside pressure to push the liquid up into your mouth. That's the basic principle behind how straws work. Even if you could create a perfect vacuum inside the straw, the maximum height that atmospheric pressure can push water or soda is about 10.3 meters. That's because a column of water that tall weighs enough to exert a pressure equal to atmospheric pressure at sea level. So that becomes the limit. To summarize, straws work not because we suck liquid up, but because we create a pressure difference. The outside pressure, atmospheric pressure, does the actual pushing, and the tallest column it can push is about 10.3 meters. Beyond that, gravity wins. To understand why gases behave the way they do, we use the kinetic molecular theory. This model helps us predict gas behavior under different conditions. Like all models, it's not perfect and breaks down under extreme scenarios, but it works well for many practical purposes. The kinetic molecular theory is based on 4 key ideas. Gas particles move in constant straight-line motion. They don't attract or repel each other, they simply bounce off. There's a lot of space between particles relative to their size. The average kinetic energy of gas particles is directly proportional to temperature in kelvins. As temperature increases, particles move faster and carry more energy. This model explains several properties of gases. Gases are compressible because of all the empty space between particles. Gases take the shape and volume of their container because they're always moving. And gases have low density compared to solids and liquids because their particles are so spread out. Let's look more closely at compressibility. Gases can be compressed easily because their particles are far apart. When we reduce the volume, we're simply squeezing those particles closer together. Liquids, on the other hand, have very little space between particles, which is why they resist compression. Because gas particles move freely and interact very little, they spread out and fill the entire volume of their container. They also take its shape. This is different from solids, which maintain shape and volume, and liquids, which maintain volume but not shape. Gases have much lower density than solids or liquids. For example, if you converted the water in a typical soda can to steam, it would fill about 595 liters, or roughly 1,700 soda cans. That's how much space gaseous particles occupy compared to when they're in the liquid state. The kinetic molecular theory helps explain why gases behave the way they do in daily life. It helps us understand why inflating a balloon works, why our lungs can expand and contract, and how gases fill containers regardless of their shape. Pressure is created when gas particles constantly collide with the walls of a container. These collisions exert force, and pressure is just force per unit area. Everyday phenomena, like using a straw, inflating a ball, or breathing, all rely on gas pressure. When you climb a mountain or fly in an airplane, the air becomes thinner, there are fewer molecules per volume. This results in lower pressure. That's why your ears pop. The internal pressure in your ears doesn't match the dropping external pressure, causing discomfort until equilibrium is restored. The pressure a gas exerts depends on how many particles are present in a given volume. More particles mean more collisions and therefore higher pressure. Fewer particles mean fewer collisions and lower pressure. To sum up, pressure increases when we add more gas particles to a fixed volume. That's because more collisions occur. This principle is essential when we fill tires, adjust medical gas tanks, or calculate oxygen delivery in healthcare settings. Let's now look at how we measure pressure. One common unit is the atmosphere, or ATM, which is the average pressure at sea level. The SI unit is the Pascal, Pa, defined as 1 Newton per square meter. Note that 1 ATM equals 101,325 pascals. Another unit of pressure is millimeters of mercury, or mmHg, which comes from the height of a mercury column in a barometer. Atmospheric pressure at sea level can push mercury up to 760 mm high. Since mercury is much denser than water, this unit provides a convenient way to measure pressure. Millimeters of mercury are also referred to as torr, named after Evangelista Torricelli, who invented the barometer. So 1 ATM is equivalent to 760 mmHg, or 760 torr. You may also encounter other pressure units like inches of mercury, inch Hg, and pounds per square inch, psi, especially in clinical and engineering settings. This slide summarizes the most commonly used pressure units. Make sure you're comfortable converting between ATM, Pa, mmHg, torr, and psi. These conversions are essential for solving gas law problems and are often found inside the back cover of your textbook. Let's practice converting between units. If you're given a pressure in atmospheres and asked to convert it to mmHg, just multiply by 760. For example, 0.311 ATM is equal to 0.311 x 760 mmHg, which gives us 236 mmHg. Being able to move between units like this is a key skill. Most airplanes fly between 25,000 and 40,000 feet, where atmospheric pressure is less than half of what we experience at sea level. At such low pressure, our bodies can't get enough oxygen. The effects include dizziness, shortness of breath, and even unconsciousness. That's why cabins are pressurized and oxygen masks are available for emergencies. Airplanes pressurize cabins using part of the engine system. As air enters the jet engines, turbines compress it. Most of the air exits as thrust, but some is directed into the cabin. It's cooled, mixed with cabin air, and cycled. The pressure is regulated to be equivalent to an altitude of about 8,000 feet, or roughly 0.72 ATM, which keeps passengers safe. Now let's talk about Boyle's law. It describes the inverse relationship between pressure and volume of a gas, assuming constant temperature and number of gas particles. When volume goes down, pressure goes up, and vice versa. This principle is essential for understanding breathing syringes and medical devices. Think of a bike pump. When you pull the handle up, the volume increases and the pressure inside decreases, drawing in air. When you push down, the volume decreases, the pressure rises, and air is forced into the tire. This illustrates Boyle's law in action. Robert Boyle discovered this relationship in the 1600s. Boyle's law tells us that pressure and volume are inversely proportional as long as temperature and number of particles stay constant. We express this mathematically as V is proportional to 1 over P. This slide shows two things. First, a J-tube demonstration where adding mercury increases pressure and decreases gas volume. Second, a graph of volume versus pressure. You'll see that as pressure increases, volume decreases in a curved relationship. This is the hallmark of an inverse proportionality. Kinetic molecular theory explains why Boyle's law works. When we reduce volume but keep the same number of gas particles, they collide with the container walls more frequently. More collisions mean more pressure. So the increase in pressure is a result of decreased volume causing increased particle collisions. Scuba divers must understand Boyle's law. As they dive deeper, water pressure increases, compressing the air they breathe. Regulators on scuba tanks adjust the pressure of the air delivered to match the surrounding water pressure. Without this adjustment, divers couldn't breathe. At a depth of 20 meters, the surrounding pressure is about 3 ATM, 1 ATM from the atmosphere and 2 ATM from the water above. To inhale, the diver's regulator delivers air at 3 ATM to match the external pressure. This allows normal breathing under high-pressure conditions. Now, what happens if a diver ascends quickly while holding their breath? The air in the lungs, compressed to 3 atm at depth, suddenly finds itself at 1 atm at the surface. According to Boyle's law, the volume would triple. This rapid expansion can cause serious lung damage or even death. That's why slow ascents and continuous breathing are critical for diver safety. This slide explains the calculation behind the danger. If a diver breathes air at 3 atm and rises to 1 atm without exhaling, the air volume in their lungs would increase threefold. This shows the potentially fatal consequences of ignoring Boyle's law underwater. Let's apply the math. A cylinder contains gas at 4.0 atm in a volume of 6.0 liters. If the pressure drops to 1.0 atm, what's the new volume? Using the formula P1V1 equals P2V2, we solve for V2. V2 equals 4.0 atm times 6.0 liter, divided by 1.0 atm, which equals 24.0 liter. So the gas expands significantly when pressure decreases. This skill builder question provides more practice. If a syringe of air goes from 16 ml to 7.5 ml under pressure, what is the pressure at depth? Use Boyle's law again to find it. Then, using the pressure increase of 1 atm per 10 meters, you can estimate the snorkeler's depth. Cartoons like the Flintstones show characters snorkeling with impossibly long reeds from deep water. But could that actually work? The answer is no. Despite what cartoons show, our lungs can't pull air from the surface once the water pressure becomes too high. At 10 meters of depth, the external pressure is 2 atm. If your snorkel extends to the surface where the pressure is 1 atm, you'd be trying to inhale air at lower pressure than your lung surroundings. Instead of air entering, it would be forced out. This is why divers use tanks, not long snorkels. Let's shift to Charles's law, which describes the relationship between gas volume and temperature. Hot air rises because heating a gas causes it to expand. When volume increases and mass stays the same, density decreases and less dense gases rise through more dense ones. Think of a hot air balloon. Heating the air inside the balloon causes it to expand. As the volume increases, the density drops and the balloon becomes lighter than the surrounding cooler air. That's why it floats upward. This is Charles's law in action. To see Charles's law in action, we can conduct an experiment, keep the pressure of a gas constant, and measure its volume at various temperatures. When we plot these values, we'll observe how the volume changes with temperature. This helps us understand the direct relationship between them. When we graph the results, we see a linear relationship. As temperature increases, volume increases. If we extrapolate the line backward, we hit a temperature at which the volume becomes zero. This occurs at negative 273 degrees Celsius, or 0 K. This is absolute zero, the coldest temperature possible, where molecular motion theoretically stops. This relationship was first described by Jacques Charles, a French physicist. His law states that the volume of a gas is directly proportional to its temperature in kelvins, assuming constant pressure and number of particles. Mathematically, we write it as V1 over T1 equals to V2 over T2. In a direct proportional relationship, increasing one variable increases the other. So if the temperature of a gas is doubled in kelvins, the volume doubles. Triple the temperature and volume triples. This behavior aligns perfectly with kinetic molecular theory. As temperature rises, gas particles move faster and need more space. Let's look at what's happening at the molecular level. If you move a balloon from ice water to boiling water, the gas particles inside it gain kinetic energy and move faster. This causes the balloon to expand. If the pressure remains constant, the only way to accommodate the higher energy is by increasing volume. We can use Charles's law in both directions, to find the new volume after a temperature change or to find the new temperature after a volume change. Just remember, temperature must always be in kelvins. This is critical for accuracy in gas law calculations. Let's work through an example. A gas has a volume of 2.80 L at an unknown temperature. When cooled to 0 degrees Celsius, 273 K, its volume decreases to 2.57 L. We're asked to find the original temperature in both kelvins and Celsius. Use the formula Phi1 over T1 equals to V2 over T2 and solve for T1. Using the equation T1 equals V1 times T2, then divided by V2. We plug in our values, 2.80 liters times 273 K divided by 2.57 liters, which gives us T1 equals approximately 297 K. To convert this to Celsius, subtract 273, so T1 equals approximately 24 degrees Celsius. Always remember work in kelvins during the calculation, then convert to Celsius if needed at the end. So far, we've looked at relationships between two variables at a time, Boyle's law and Charles's law. But what if pressure, volume, and temperature all change at once? For that, we use the combined gas law, which merges the previous two, P1 times V1 over T1 equals 2, P2 times V2 over T2. You use the combined gas law when dealing with a single gas sample undergoing simultaneous changes in pressure, volume, and temperature. It's extremely useful in real-life scenarios such as adjusting ventilators, understanding lung expansion under variable conditions, or working with gas cylinders in healthcare settings. Let's go through an example using the combined gas law. A gas has an initial volume of 158 ml at 735 mmHg and 34 degrees Celsius. It's compressed to 108 ml and heated to 85 degrees Celsius. We're asked to find the final pressure. This problem involves changes in pressure, volume, and temperature, so the combined gas law is the right tool. Now let's introduce Avogadro's law. What happens if we change the number of gas particles? If we keep temperature and pressure constant, the volume of a gas increases as we add more moles of gas. In other words, volume and moles are directly proportional. This relationship was first formally proposed by Amedeo Avogadro. His law says that volume is directly proportional to the amount of gas in moles, assuming constant temperature and pressure. Mathematically, V1 over N1 equals to V2 over N2. Imagine blowing up a balloon. As you exhale into the balloon, you add gas molecules to it. This increases the number of moles of gas, and the volume of the balloon increases accordingly. That's Avogadro's law at work. Here's an example. A 4.8 liters sample of helium contains 0.22 moles. What amount of helium should be added to increase the volume to 6.4 liters? We're given the initial volume in moles and a final volume. Use V1 over N1 equals V2 over N2 and solve for the final number of moles. Solving for N2, we get 0.22 moles times 6.4 liters divided by 4.8 liters equals to 0.293 moles. Since the balloon already contains 0.22 moles, subtract that from 0.293 to find how much more you need to add, 0.073 moles. This shows how we can predict gas volume changes based on the number of particles. Now we combine everything into one equation, the ideal gas law. PV equals to nRT. This equation includes pressure, volume, temperature, and number of moles. The constant R ties all the variables together and must match the units used. Make sure to use consistent units. Pressure P in atmospheres, volume V in liters, temperature T in kelvins, amount N in moles. R is the gas constant and has a value of 0.0821 LATM per mole times K. Table 11.2 summarizes the relationships among the simple gas laws, Boyle's, Charles's, and Avogadro's, and shows how they are integrated into the ideal gas law. Let's solve a sample problem using PV equals to nRT. You're given 0.845 moles of nitrogen gas at 1.37 atm and 315 K. What's the volume? Rearrange the equation to solve for VV equals to nRT over P. Then substitute the values and solve. When you plug in the numbers, you get a volume of approximately 16.0 liters. Always check your units and reasonableness. Since 1 mole of gas at STP occupies 22.4 liters and our conditions are fairly close to standard, this answer makes sense. The ideal gas law is powerful and widely used in chemistry and clinical settings. We can also use the ideal gas law to calculate the molar mass of an unknown gas. If we know the mass of a gas sample and use PV equals to nRT to find the number of moles, we can divide the mass by the moles to get molar mass. This technique is useful in identifying gases or verifying the purity of a sample. Let's walk through an example. A gas sample has a mass of 0.136 grams, occupies 0.112 liters, and is at 298 K and 1.06 atm. First, use the ideal gas law to find the number of moles, then divide the mass by the number of moles to find the molar mass. This approach connects chemical identity with physical behavior. It's important to know that real gases don't always behave ideally. Under high pressures or very low temperatures, gas particles start to interact with each other or occupy significant space, which causes deviations from ideal behavior. For most everyday conditions, however, the ideal gas law gives accurate results. Now let's discuss gas mixtures. According to kinetic molecular theory, each gas in a mixture behaves independently of the others. The pressure it contributes is called its partial pressure. The total pressure of a gas mixture is the sum of all the partial pressures of its components. To calculate a partial pressure, multiply the fractional composition of the gas by the total pressure. For example, if oxygen makes up 21% of air and total air pressure is 1 atm, the partial pressure of oxygen is 0.21 atm. This concept is critical in medicine, especially in oxygen therapy and anesthesia. Dalton's law states P total equals P1 plus P2 plus P3 plus. For air at 1 atm, P underscore total equals to 0.78 atm N2 plus 0.21 atm O2 plus 0.01 atm R equals to 1.00 atm. Each gas exerts its own pressure independent of others in the mixture. This is foundational for understanding respiratory gas exchange. Here's an example. A mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. If the partial pressure of helium is 341 millimeters of mercury and neon is 112 millimeters of mercury, the pressure of argon is simply P argon equals to P total minus P helium minus P neon, which equals to 558 minus 341 minus 112 equals to 105 mmHg. Our lungs are adapted to breathe oxygen at a partial pressure of about 0.21 atm, the level found at sea level. As total pressure decreases at high altitudes, the partial pressure of oxygen drops too. At the summit of Mount Everest, total pressure is only 0.311 atm and oxygen's partial pressure is just 0.065 atm, leading to hypoxia or oxygen deprivation. Too much oxygen can be just as dangerous. At 30 meters depth, a diver breathes air at 4 atm. That gives a PO2 of 0.84 atm, significantly higher than normal. When PO2 exceeds 1.4 atm, oxygen toxicity can occur, leading to tunnel vision, convulsions, and even death. Divers must manage depth and gas mixtures carefully. This slide reinforces the concept of oxygen toxicity. While oxygen is essential, high concentrations under pressure can disrupt body functions. It's a powerful example of how pressure and gas behavior intersect with physiology, and why understanding partial pressures is so important in both medicine and diving. Our lungs are also adapted to breathe nitrogen at a partial pressure of about 0.78 atm. At 30 meters depth, a diver breathes nitrogen at over 3 atm. This increases nitrogen's concentration in body tissues, and when PN2 exceeds about 4 atm, it can cause nitrogen narcosis, also known as rapture of the deep. This condition impairs judgment and creates a state similar to intoxication. To avoid both oxygen toxicity and nitrogen narcosis, deep-sea divers use special gas mixtures like Heliox, a blend of helium and oxygen. Helium is less dense and does not cause narcosis. Heliox contains a reduced amount of oxygen to keep PO2 within safe limits. Dive shops calculate the best mixture based on intended depth and duration. Let's walk through an example of calculating partial pressure, total pressure, and percent composition. Recall that the partial pressure of a gas in a mixture is equal to its fractional composition multiplied by the total pressure. So to find the partial pressure of O2, we simply multiply its fraction in the mixture by the total pressure. When a gas is collected over water, some water vapor mixes in. The total pressure of the gas mixture includes the vapor pressure of water, which depends on temperature. For accurate results, we subtract the water vapor pressure from the total pressure to get the pressure of the dry gas. Here's an example. Suppose hydrogen gas is collected over water at a total pressure of 758 millimeters of mercury and 25 degrees Celsius. The vapor pressure of water at 25 degrees Celsius is 23.8 mmHg. To find the pressure of hydrogen alone, subtract pH 2 equals 758 mmHg minus 23.8 mmHg, which equals 734 mmHg. Gases often appear in chemical reactions. Instead of measuring mass, we can work with gas volume, pressure, and temperature. Using the ideal gas law, we can convert between these physical quantities and moles and then use stoichiometry to determine how much of another substance is involved. For example, how many moles of ammonia, NH3, form from 2.5 L of hydrogen gas at 1.32 atm and 381 K, assuming excess nitrogen? First, use PV equals nRT to find the number of moles of H2. Then use the balanced chemical equation to convert to moles of NH3. This is a classic application of stoichiometry with gases. At standard temperature and pressure, STP, which is 0 degrees Celsius and 1 atm, 1 mole of any ideal gas occupies 22.4 liters. This is known as the molar volume. We can use this value as a conversion factor in calculations, which greatly simplifies stoichiometric problems involving gases. This slide reinforces the concept that 1 mole of any gas at STP occupies 22.4 L. Regardless of the type of gas, helium, oxygen, carbon dioxide, the volume per mole is the same under standard conditions. This uniformity is a key strength of the ideal gas law. Let's apply that to a reaction. If 0.879 moles of CaCO3 decompose to form CO2, how many liters of CO2 are formed at STP? Multiply 0.879 moles by 22.4 liter per mole to get approximately 19.7 L. This direct conversion makes gas stoichiometry much more manageable. Now let's shift to environmental chemistry. Air pollution is a serious issue linked to energy production, transportation, and industry. Some key pollutants include SO2 from electricity generation and metal refining, an irritant and acid rain precursor. CO from vehicle emissions, a gas that binds to hemoglobin and deprives the body of oxygen. Continuing with major pollutants, ozone, O3, is beneficial in the upper atmosphere but harmful at ground level. Ground-level ozone forms when sunlight reacts with vehicle emissions and causes lung irritation and long-term respiratory issues. Nitrogen dioxide, NO2, another harmful pollutant, comes from vehicles and power plants. It's responsible for the brown haze seen in cities and is a precursor to acid rain. Thankfully, regulation has made a difference. Starting in the 1970s, the Clean Air Act and its amendments set limits on pollution levels. Since then, pollutant levels have dropped significantly in many U.S. cities, even as the number of vehicles has increased. This is a strong example of how science-based legislation can protect public health. While progress has been made, pollution still poses risks in many urban areas. Ozone levels in particular can exceed safe limits, especially during hot summer months. Continued awareness and action are needed to further reduce air pollution and protect respiratory health, especially for vulnerable groups like children and the elderly. To review, the kinetic molecular theory explains gas behavior in terms of particle motion. Pressure results from gas-particle collisions. We covered Boyle's, Charles's, and Avogadro's laws and how they combine in the ideal gas law, PV equals nRT. We explored partial pressures, gas stoichiometry, and environmental applications. Be sure to refer to Table 11.2 in your book for a summary of all gas laws. By now, you should be able to convert between different pressure units. Apply simple gas laws like Boyle's and Charles's. Use the combined gas law when multiple variables change. Use the ideal gas law to calculate pressure, volume, temperature, or moles. Relate total pressure and partial pressures in mixtures. Solve stoichiometry problems involving gaseous reactants and products. These skills are essential for both your academic success and your future career in healthcare.